Hi, AP Calc class. So this is our very last new lesson. We are officially done and we get to start reviewing for the AP test. So exciting. All right, so I just like memes, so I have a few memes on this lesson. All right, so the last type of volume problem is different than the others. So volume of a solid using slicing, if for each x, the area of the cross-section of a solid is known and continuous, then the volume is the integral of a of x. So this one's different. Notice there's no reference to rotation. We're not rotating anymore. So imagine that each cross-section is the base of the shape. So like if this is my area, right? That's my cross-section. And then imagine there's a figure shooting out of it. Like, so we could have like a square, right? So there's all these squares, and the cross section's the base of the square. So it's this weird looking shape where imagine coming out of the paper is a bunch of squares, and it creates this region. So let's look at a picture. Oh, I guess I don't have a picture on this one. I do have another video for you guys for tomorrow. So let's talk about the a of x. So in all the other problems, because they were circles, we were integrating the area of a circle. But now we need to think about what's the area of a square. So if this is a square, what's that distance? That's just your top minus bottom, right? So square root of x minus x squared. That's the side of the squared, of the square squared, right? So it's top minus bottom squared. Or right minus left if we're talking in terms of y. Now the semicircle, imagine we have, this is the base of the semicircle, and then we have that distance coming out. All right, so we have all these like semicircles popping up. Now this one, the semicircles I think are actually the hardest. What is that distance then? So my top minus bottom is no longer my radius, right? Like it was before. That's actually my diameter. So diameter equals my square root of x minus x squared, which means what's the radius? The square root of x minus x squared all over 2. So now here's the thing. When we integrate that, it would be the integral of pi r squared. So top minus bottom all over 2 squared. So we end up getting 2 squared is 4. So you end up getting pi over 4 on the outside. And then the integral top minus bottom squared. But notice the whole thing is being squared. It's not like our big R squared minus little r squared. It's their difference is being squared. So because that's the diameter instead of the radius, we have to divide by 2. Right? We would divide by 2. The whole thing gets squared, which means you end up with that pi over 4 on the outside. Because it's really, you have that 1/4. All right, and then the last one that we're going to talk about, and these are just the most common. You can have other things, and you will see other types. These are just the ones that are the most common. Okay, so this last one is an equilateral triangle. So imagine for this one, we have this, and then we have like, wow, that's really pretty, a triangle popping out at us. And that's the base of it. Now, go back to trig. The easiest way to figure out the area of an equilateral triangle is our trig formula. So if you remember, the area of a non-right triangle is 1/2 sine of A times AB. Or BC, I don't know. So if you have an equilateral triangle, right? That means all of these are the same. What's the angle? 60. So the area of an equilateral triangle is 1/2 sine of 60 times a squared. What's sine of 60? Root 3 over 2. So we actually get root 3 over 2 a squared. So it'll be root 3 over 2. The a is again that top minus bottom squared. So this is for our equilateral triangle. So equilateral triangle, semicircle, square. All right. Do you need to memorize these formulas? I wouldn't say necessarily memorize them, but understand where they came from. Like, look at my math. Make sure you understand. I spelled diameter really bad. I'm just shameful sometimes with my spelling. Not that I don't know how to spell diameter. Oh, all right. Yeah, I wouldn't say memorize these, but understand, like go through this process and understand so that you can do this if you need to. All right. So here's a really good picture of the squares. So we have our square root of x. We have y equals 1/8 x squared. They're showing you where they intersect, and you can actually set them equal and solve. It's really not that hard. So find the volume of a solid whose base is r if slice is perpendicular to the x-axis. So notice I highlighted that. That means our functions are in terms of x. Functions in terms of x. All right, so I'm doing in the area of a square, so no pi. My x's are going from 0 to 4. What's my top function? So this one's kind of hard because it's on the side. I'm going to draw a different picture for myself. Square root 1/8 to the, okay. So my square root is on top. My 1/8 x squared is on the bottom. So that's the whole distance. So square root of x minus 1/8 x squared squared. Because this is your side squared, and the area of a circle is side squared. Okay, put that in the calculator. What do we get? And I got 2.057. Yeah, these are very rarely not without a calculator. Pretty much these are always a calculator problem. Okay. All right, so now we're going to do the same problem, but perpendicular to the y-axis. So I'm going to draw this again. So I've got my square root, my 1/8 x squared, and my square root of x. Now we need to solve those. So if y equals the square root of x equals y squared. So I'm going to write that right underneath. So this is y squared. Right? And then 1/8 x squared equals y. X squared equals 8y. X equals the square root of 8y. So this is the square root of 8y. All right. So now for this one, when we're doing this in terms of y, our cross section is going right to left. So that's the base, right? And I have my square just like popping out. Right? So down here it's smaller and it's popping out. All right. So that now when we're doing it in terms of in terms of y, we need, instead of top minus bottom, it's right minus left. So what's our right, the function on the right of the graph? The farthest right is over here, and that's our 8, the square root of 8y. Minus my left function, which is y squared. And then squared, right? Side squared, that's the area of a square. And then my bounds now, it's in terms of y, so instead of 0 to 4, it's 0 to 2. Plug this in the calculator, and I got 2.667. It looks like 2.6 repeating, but then there's also this 877 at the end, so it's not quite exactly 2 2/3. All right, that's it. Okay. Slightly different problem, but we are doing this in terms of the y-axis. So we're going to do squares, y-axis. So pause the video. Try to set this problem up on your own. So I've got my parabola, x equals 2, and y equals 0. Remember, y equals 0 is the x-axis. So that's my region. So we're doing this in terms of y, or in terms of x, since it's y-axis. So x equals the square root of y. So that means we're going to do right minus left when we do these. This point is 2, so it's going to be 2 comma 4. So my y's are going from 0 to 4. Right minus left, right is the 2 minus the square root of y squared. What do we get? Again, just plug this. You could do this one. I wouldn't say don't do this one by hand. I mean, I don't really see the point. This is definitely something you could do without a calculator. That's easy enough to multiply out. But I'm just going to use a calculator for it. And I got 2.667, which is the same answer as the last one. Was that problem the same? They're slightly different. Same answer. My decimals at the end, though, were different. So this one ends with 369, and the other one ended with like 8 something. All right, that's it. Next one. It's going to be the same problem. We're doing 3 of the same problem. So now this one, still y-axis, but this time we're going to do semicircles. It's the exact same problem, but doing semicircles. Pause the video and try this on your own. So again, I've got this region. It's still 0 to 4. So now when we're doing this in terms of y, this is my cross section, and I have semicircles. So remember, that distance is our diameter. So on the side, I'm going to write my diameter is 2 minus the square root of y. Right, this is the square root of y. So that's my diameter, which means my radius is 2 minus the square root of y all over 2. So we're going to integrate pi r squared. So 2 minus the square root of y all over 2. So you can either integrate that, or you can make it pi over 4, the integral 0 to 4, 2 minus root y squared. And we actually already did that piece. It was like 2.6 repeating, right? So we're just going to end up multiplying that by pi over 4. So my answer, I'm going to write the answer with the just times pi and then without times pi. So this gives me 0.667 pi, or 2.094. So both of those are correct. I would give full credit for both of those. The AP test takes both of those also. All right, last one, equilateral triangle. Gee, I wonder why Ms. Vizone went over how to find the area of these 3 pieces. All right. 2. So now this time, this is our base, and we have these equilateral triangles like popping out at us. These are hard to visualize. What did people do? Before technology, I don't know what people did. All right, so my area of an equilateral triangle is 1/2 side squared, a squared, sine of 60. Sine of 60 is root 3 over 2. So we get root 3 over 4 a squared. So that's what we're integrating. No pi in this one. What happened? My root 3 over 4 disappeared. 0 to 4 a squared. So what is my a? That's this distance right in here. That's our base, and that's exactly the same as it's been in the last 2 problems. 2 minus the square root of y dy. So my final decimal for this one is 1.155. And that's it. All right, last problem. This is an AP problem, clearly. It's from 2000. So I want you to pause the video and try this whole problem on your own. So first thing we need to do is number one is not assume. This point right here of intersection, we know we need to find it. It looks like it's at 1, but it's not. Use your calculator, plug in, where are those intersecting? I'll check my notes for it. And that point of intersection is 0.94194, comma 0.4117. So that's the point of intersection, and then I stored A. And if you tell the AP people, oh, that's A, you don't have to write the decimal out. So for part A, I'm integrating the region R. Now this one, it's all going to be in terms of the x-axis. So I highlighted x-axis, x-axis. So it's just top minus bottom, 0 to A.